It's a good morning, everyone. Today we are going to start the second section on the matter and radiation module, which is the photoelectric effect. Right. So, photoelectric effect, as the name suggests, it is some phenomena related to uh, electrons, right? Electrons and photons. I think you have heard about photons and electrons already in chemistry as well. So let's see what actually what it is, right? So this photoelectric effect, this phenomena was first found by a scientist called Hertz in 1887. But it was so he saw that when electromagnetic wave such as ultraviolet light, right? Electromagnetic waves such as ultraviolet light right? Ultraviolet light falls on a metal sheet. So it's a metal. Right? When light having sufficient frequency, not all the lights, for certain light, when they are uh, directed onto a metal sheet, some uh, some kind of electric charges are emitted from it. So at the time, they didn't know that these electric charges are electrons, right? So later in 1899, J. Thomson found about this electron. So and in 1900, and this was Philip Maynard conduct the same experiment, and shown that these electric charges emitted from the metal sheet due to this electro uh, electromagnetic waves. These are magnetic waves. Due to these electromagnetic waves are electrons. Right? So basically, the idea you have to get it is photoelectric effect means the emission of electrons due to the uh, due to electromagnetic waves falls on a metal. And that's the simple idea of the photoelectric effect. The emission of electrons from a metal due to electromagnetic waves falls on a metal. Right? And these are the three scientists that I have just mentioned. Right? So this is a small experiment. This is a small experiment which can be used to measure photoelectric effect. So here is a called electroscope. So here they have two leaves. These are called leaves. Right? And this is zinc plate. So what is done here is UV rays are allowed to fall on this zinc plate, which is a metal. The UV rays are allowed to fall on the zinc plate, which is a metal. And so initially, so let's take a look. Yeah, UV rays are not yet emitted, not yet directed to zinc plate. So when this is idle without any UV rays falling on the zinc plate, so they so that these leaves are somewhat diverge from each other, right? Diverge, spread away from each other due to this negatively charge. So we know from electrostatic fields, the negative charges or positive charge, like charges repel, whereas unlike charges attract. So here, these leaves are initially negative charge. So these two leaves, so these two leaves can rotate around this point. Rotate means they can move, right? Inclination can be changed. So initially they are far away due to this negative charge. Due to this negative charge, repel forces acts on these leaves and they are spread away, diverge from each other. And then UV rays are initially initially uh, sink no UV rays initially no UV rays are directed towards zinc plate and directed towards zinc plate and the leaves are negatively charged. Negatively charged. So they are diverged from each other. But then these UV rays are directed at zinc plate. So are allowed to fall on zinc plate. Allowed to fall on zinc plate. And they observed that these two leaves and these two leaves they get converge or they get closer together. And they get closer together like this. And they converge towards each other. It was observed that the leaves are converged. Converged. The leaves are converged towards each other. The leaves are converged towards each other. Uh, the reason is the emission of electron. When UV rays are allowed falls on zinc plate, here you can see the electrons are emitted. So the number of electrons residing on this electroscope gradually decreases, and the number of electrons on these leaves decreases. The repelling forces decreases, so they get converged. Because as UV rays falls on zinc plate, electrons are emitted from electrons are emitted from zinc plate. Right? Electrons are emitted from zinc plate. So the repelling forces repelling force between the leaves decreases, so they get converged. Right? So they get converged. So this is a very small method to measure the photoelectric effect when a zinc plate or any metal is subjected to UV rays with sufficient frequency, the electrons are emitted. So from the above experiment, from the above experiment, from the above experiment, photoelectric effect can be uh, verified. So photoelectric effect says that photoelectric effect says that when photoelectric effect says that when electromagnetic waves having sufficient frequency. Not all the electromagnetic waves does this effect. Electromagnetic wave have sufficient frequency, falls on metal plate, waves having sufficient frequency, falls on a metal plate, the electrons are emitted. Electrons are emitted from the plate. Right. Let's do a small demonstration of photoelectric effect using a photocell. Just a photocell is a small vacuum, small tube which consists of a cathode and anode, and it is uh, fully vacuum. Photocell is a photocell is a uh, photocell is a vacuum tube consist of consist of metal metal anode and a cathode made of alkali material like cesium or potassium. But so and the reason behind uh, right. So it is vacuum. Right? It is a vacuum, basically a vacuum tube. So reason behind this of being a vacuum is to reduce the interference. Right? Reduce the interference to electron flow. Right. So tube is vacuum. Tube is vacuum to tube is vacuum to decrease the interference when electrons are emitted due to photoelectric effect. Right, so when the electrons are emitted and moving, if there is very big interference. If the surrounding is filled with some other particles, unwanted particles, like air particles, then these electrons would lose their energy more quickly. That in order to mitigate that, the tube is emitted due to electric effect. Right, so this is the basic setup. We have, so this is a photo cell. Which is fully vacuum. Right, so milliammeter is connected in in series to measure the current. And a voltmeter is also connected in parallel to measure the voltage difference. So these are two metal plates. This is cathode. Anode. Right? Cathode and anode. Right. So when here some electromagnetic wave falls having some frequency is an electromagnetic wave falls on the cathode. And so here it was observed that when even though external external voltage is applied to the photons, all the photons, total apparatus, right? Even though no right, even though no even though no external voltage applied, no external voltage applied, when electromagnetic waves have sufficient frequency, having sufficient frequency falls on the cathode, current that's so this should be connected using a wire. A current flows through the circuit. A current flow through the circuit, right? Current flow through some constant current flow through circuit I. This is called photocurrent. And this current is called the photocurrent. called the photocurrent. Yes, it's called the photocurrent. And so this is what happens when no external voltage is applied. And then see what happens when an external voltage is applied. Like this, right? So what happens when a battery is connected to the circuit? And so when a battery is connected to the circuit, thus that the positive terminal is connected to the anode. Right? So electrons are emitted here and they are attracted towards the anode. Right? So here the intensity is constant. Intensity means number of keeping the intensity constant. The number of electrons. Intensity number of electrons emitted per unit time. Here intensity is the number of waves falls on the cathode per unit area per unit time. Is the number of waves falls on the cathode per unit area per unit time. And so it is kept constant. And the intensity is kept constant. Intensity is kept constant. So when the intensity is kept constant, and potential is varied. So we can change the potential by, so here it is. So instead there is a variable voltage source, resistor, and sliding key is there. By varying sliding key, by adjusting the sliding key, the potential can be changed. And it is it kept constant. The applied voltage is changed. On the photo cell, positive manner. So the photocurrent and the voltage, the graph of photocurrent against the graph of photocurrent against voltage is as follows. So it is almost constant. Right? So V AC, right? Voltage of anode with respect to cathode. Voltage of anode with respect to cathode when it is positive. Anode and with respect to cathode. So this is a photocurrent. So you can see it is almost constant. And although the voltage of anode is increased, the photocurrent doesn't vary. Right? So photocurrent doesn't affect on the voltage. Normally, when we know when voltage we consider passive resistor, when voltage is increased, the current from the resistor increase. But here doesn't happen. When voltage across the photo cell is increased, nothing happens to photocurrent. When the constant intensity, the constant light intensity. Right? Then next practical is, so what happens when if the terminals of the battery is reversed? And then what would happen to the photoelectric current when the reverse voltage of the photo cell is increased? When the When negative voltage is applied on the photo cell, is applied on the photo cell and vary. The positive terminal should be towards the cathode. Right. So in that case, what happens? So electrons are emitted. Now this is positive charge. This is negative charge. So here you can see the emitted electrons are attracted towards the cathode again due to the positive charge. Here the emitted electrons are attracted towards, here the emitted electrons are attracted towards the cathode again, cathode again, cathode again. So the electrons are decelerated. That electrons are decelerated. Decelerated. But it is observed the photocurrent doesn't become zero suddenly. Does not become zero suddenly. Does not become zero suddenly. It gradually only decreases to zero. Zero when voltage is increased in negative manner. It doesn't come to zero suddenly. It decreases, but not suddenly come to zero. Gradually comes to zero. Right, so Vs. Right, so this is the variation photo current. and VAC. Voltage of anode. Let's just say cathode. Now cathode is having higher voltage than the anode. Right. So cathode is having higher voltage than the anode because positive terminal is connected to the cathode. VS is negative. And VAC is increased in negative manner. The photocurrent comes to zero at a particular value. Right. So the voltage where photo current becomes zero, current becomes zero is called as stopping voltage. Now zero is called the stopping voltage. Stopping voltage at this stopping voltage the electron having the highest velocity also highest velocity. The electron having the highest velocity also uh, decelerate and comes to rest. Comes to rest before reaching the anode. Anode. Uh, so the photocurrent becomes zero. Right. So in that case, if the maximum potential energy if maximum kinetic energy is Kmax, maximum kinetic energy Kmax, and stopping voltage is, let's say, Ps. So is the cathode, anode. So I'm considering electron initially having Kmax of kinetic energy. right? And here comes to 0. Here we assume when the electron is reached to the other side, kinetic energy becomes 0. So from conservation of energy, conservation energy. So here what has happened? Conversation. Uh, Kinetic energy is used to do the work against the electric field. Is used to do work against of electron. Is used to do work against the electric field. So K max. K max is the maximum kinetic energy. Work against the electric field. E Vs. And so V is the stopping voltage. Right, so some observations from the above. Right, so when so first of all, so when these two graphs are combined, we can draw a total graph of the photo cell under positive and negative voltage uh, differences. So by combining, right, so 1 and 2 graphs, we have this full graph. Right, so VAC voltage, photo, photocurrent. Right, so this is under constant intensity. And this is under constant intensity and frequency. Constant intensity and frequency. Constant intensity and frequency. Next, let's see what happens when the under constant frequency and varied intensity. Under constant frequency of electromagnetic waves and different intensities. And different intensity, let's say I1, I2, and I3. One is greater than I2, I3. So the graph between the photocurrent and photocurrent. That's what would vary like this. I1 having the highest intensity means higher current, higher photocurrent. I3 is the lowest, but the frequency is kept constant. So the stopping voltage remains same. All these the stopping voltage remains same. So here the important consideration is the photocurrent. Because photocurrent depends on the intensity of the electromagnetic waves, which means number of electromagnetic waves falls on unit area per unit time. And stopping voltage doesn't depend on the intensity. Next graph is let's see what happens when under constant intensity but different frequency. Under constant intensity but different frequency. Under constant intensity but different frequency. ESC. Constant in a different frequency. Let's say frequency 1 is highest, 2 is then, 3 is lowest. So photocurrent remains same because the intensity is constant. But this varies. This is the stopping voltage referred to the frequency tree. This is the stopping voltage referred to the stopping voltage 1. So the wave having the highest frequency needs the highest potential, stopping potential to keep the current at 0. And so which means when the frequency is increased, the energy of electrons, kinetic energy, maximum kinetic energy also increases. Right. Right. So in the let's see yes, the variation of uh, stopping voltage with the frequency. Frequency of electromagnetic wave. So is a stopping voltage with frequency hertz. That's what is called F no. threshold frequency, right? So there is a minimum frequency. So threshold frequency is the frequency at which the stopping voltage is zero. Right? Threshold frequency. Notice threshold frequency where the stopping voltage is zero, which means if of if electromagnetic waves having f naught of frequency is directed onto the metal plate, it would emit an electron having zero potential. Zero potential, which means zero kinetic energy. That's zero kinetic energy. Right? So the f naught, the frequency is just sufficient enough to emit an electron, not to give any potential, not to give any kinetic energy to the electron. So f naught is called the uh, f naught threshold frequency. Threshold frequency. Threshold frequency. So for different metal, this threshold frequency also different. Dash. Threshold frequency is the minimum. Threshold frequency is the minimum amount of frequency of electromagnetic waves wave in order to emit an electron. With zero kinetic energy. With zero kinetic energy. So when uh, electromagnetic wave having threshold frequency is hit on a metal plate, it will emit an electron zero kinetic energy. So that energy possessed by the electromagnetic wave is just enough to emit an electron, giving uh, kinetic energy. Right. So some common for Ke also we can have the same graph. For different metals, threshold frequencies are different. Right, so these two are different metals. Different metals. Right, since K kinetic energy proportional to the stopping voltage, right, the graph of the frequency versus the graph of the kinetic energy versus the stopping voltage also look similar. Events. So some important as for some important facts. Some important facts about about graphs are as follows. Some important things about about graphs. The photo current only depends on the intensity. The photo current only depends on the intensity of light falls on the cathode. And the stopping voltage only depends on the frequency. Frequency of electromagnetic wave. Right? Frequency of electromagnetic wave. Then this threshold frequency. Threshold frequency depends on the type of metal. Type of metal. Type of metal. The maximum kinetic energy. The maximum kinetic energy of an electron depends on the difference between the frequency of the frequency of the wave and frequency of the wave and threshold frequency. And threshold frequency. Right, and another important consideration is photon. The emission of electrons is a very instantaneous process. So just when electromagnetic force is on a cathode, it will immediately like design just instantaneous. Photoelectric effect happens. The photoelectric effect happens instantaneously. The photoelectric effect happens instantaneously. So within 1 nanoseconds. It's an instantaneous process. Right? So this phenomenon, right? So normally in previous cases, we learned that in waves and oscillation section, light electromagnetic waves. So we studied the behavior of electromagnetic wave. We consider them as just pure waves. But here, these incident, mainly the photoelectric effect, right? Photoelectric effect. Right? The scientists were unable to explain the photoelectric effect using the properties of wave. Properties of wave. Why? So, for example, uh, in waves, so intensity, the energy in waves, the energy is corresponding to the amplitude of the wave. That square of the amplitude of the wave. So amplitude means the uh, number of waves. That totally depends on the number of electrons traveling. But here we can see the intensity, although the intensity is decreased. Sorry. Yes, although the intensity is increased or decreased here, the stopping voltage or the kinetic energy, maximum kinetic energy of the particle does not change. So that contradicts with the normal wave. But if there are higher number of waves traveling per unit area, definitely the kinetic energy is higher. Okay? But here that doesn't happen. So uh, any different light intensity, keeping the frequency constant, the stopping voltage is remains same. So here the kinetic energy of the particles depends on the frequency of the wave. The kinetic energy of the electron totally depends on the frequency of the wave. And that is one contradiction between this photoelectric effect and the behavior of waves. Another one is, so here finally we do the photoelectric effect happens instantaneously. Instantaneously. Photoelectric effect happens instantaneously, which means uh, within a fraction of time, right? Suddenly it happens. But in order to break, if we consider a wave, so normally the electrons are emitted by breaking the interatomic bonds between the nuclei and the electron. So in order to uh, break interatomic bond, uh, sufficient amount of energy is required. Sufficient amount of energy means the wave should travel for sufficient amount of time. Also, the wave should fall on the bond for sufficient enough of time, then the bond would absorb energy from the wave and the bond would be broken. But here the photoelectric happens instantaneous. Very quickly the bond is broken and the electron is emitted within 1 nanosecond. that also contradict with the behavior of waves. So therefore, these electrons, the concept of energy packets. Right? So these waves are now considered, can be considered the concept another method perspection of looking at waves is as energy packet or called photons or called photons. And so that was first described by Max Planck. Another perspective of looking at electromagnetic waves as energy packets, photons or photons, energy packets or photons. If the frequency of a wave is f, at here it's simply the electromagnetic wave consists of millions of energy packets, small particles, right? Particles. Right? If the frequency of a wave is f, the energy of a photon is hf. Energy of photon is hf. H is the Planck constant, S is the frequency of the electron. Right, so this was first introduced by Max Planck. Right, by building on this basic finding of Max Planck's, the Einstein. Right, so uh, Einstein gave a explanation to this photoelectric effect. He came up with an explanation to this photoelectric effect, and he got the Nobel Prize as well in 1921 for this finding. Right, so he was able to uh, describe this behavior of photoelectric effect. Right, so we know if there's a wave having having frequency f, the energy of a photon is hf, right? hf. Let's consider one. There is a positive ion, and uh, so there is a bond. Electron is bounded to this, right? And f, right, is equal hf of electromagnetic waves falls on this bond. Uh, Falls on this bond if f is greater than f naught, f naught, the threshold frequency. Yes, threshold frequency. What would happen? This bond would be broken. This bond is broken. Right, so this bond would be broken, and this electron would be thrown away. Electron is thrown away. It would be free. that electron would be thrown away with kinetic energy, say with the maximum kinetic energy. But so to break this bond, sufficient energy, some amount of energy is lost. To break the interatomic bond, sufficient amount of energy is used. And remaining energy is delivered to the electron as kinetic energy. As kinetic energy, right? That's the energy required to the energy required to break a bond is called as work function. Phi, work function phi, and it depends on the metal. At HF naught. And so the work function is equal to H into the threshold frequency of the metal. Right, so from the conservation of energy, considering these 1 and 2 figures, we can from considering conservation of energy, from considering conservation energy, we can write kmax is the difference in between these two values. Initial energy E minus the work function. That E is F no kmax. That's a normal is written as so E is equal phi plus kmax. So this is called the Newton's equation for photoelectric effect. So Newton Einstein's equation for photoelectric effect. Equation for electric effect. That if the maximum velocity of electron is V max and mass of electron is mv, me witness R MV half m V squared max. Right. So this is Einstein equation for photoelectric effect. Yes, some other important consideration is only a one electron could one photon could emit one electron from the photoelectric effect. Only single photon would emit one electron using photoelectric effect. using photoelectric effect, right? Using photoelectric, one single photon could emit one electron. Using photoelectric, not so no combination, right? Like two photons cannot emit one electron. Always so one photon could emit one electron. And there is another unit called electron volt to which we have to deal with small amount of energy. There is an energy called one electron volt to measure the amount of energy of small particles. Right, to measure small amount of energy to measure small amount of energy, a unit called a unit called electron volt. Defined. So one electron volt is equal to 10 to the power minus 19 joule. One electron volt is equal 1.610 to the power minus 19 joule. To the power minus 19 joule, right? That's another unit to measure small voltages. Now look at some examples of photoelectric effect. Let consider the following statement made by the number of electrons entered increases with the intensity of the incident light. Correct. Maximum velocity of the electrons emitted increases with the intensity of the incident light. Incorrect. Maximum velocity of the electron emitted increases with the wavelength of the incident light. Maximum velocity. So E is equal H A, and we know V is equal F lambda. Lambda. That C is equal F lambda. So F is equal CO lambda. So we can modify E is equal HC over lambda. HC over lambda. Maximum velocity of the electron increase the wavelength of the incident light. It's incorrect. Does not increase when the wavelength is increased, maximum velocity increases. So the A is correct. Electrons are emitted from a certain metal when a monochromatic light of wavelength lambda is incident on it. H is the Planck constant and C is the velocity of light. Consider the following statement. Kinetic energy of electron emitted from the metal is less than hc lambda. That is, it should be hc of lambda. Hc of lambda. Kinetic energy of electron emitted from the metal is less than this one. Yes, correct. Because this is the total energy of the photon. Some amount of energy is used to break the bond. So the kinetic energy of the electron emitted metal has less than this value. Kinetic energy of electron emitted from the metal does not depend on the material of the metal. Does depend. Incorrect. Rate of emission of electron depends on the wavelength and no, that depends on the intensity. But only A is true. A photosensitive surface illuminated separated by light of wavelength lambda 1, lambda 2, and lambda 3. Lambda 1 is greater than lambda 2, lambda 3. It means frequency is opposite, right? Frequency is opposite to lambda. And 1 means 3 is having the highest frequency. That frequency is inverse proportional to lambda. So is equal F lambda. To get the intensity, the number of photons incident per second on of the light used is kept the same value. The current voltage characteristic of photon electrons three situations are. So since the intensity is constant, photocurrent on the right plane of the this first quadrant is constant, and frequency of lambda the third wave is the highest. So F3 should be the highest. 3 should be the highest. The stopping voltage of related to uh, third wave should be the highest, and first wave should be the lowest. So this one. light of wavelength 500 Amston. So 1 Amston is 1 in 10 to the power minus 10 meters. At 1 Amston, 10 to the power minus 10 meters. Another I need to measure small lengths. Is instead on a sodium surface whose work function is 2.28 eV. The maximum kinetic energy of emitted photoelectron is. So Kmax is work function minus is at C over lambda minus the work function. H is 12.4 10 to the power 3 lambda. So this is already minus 2.28. Right, so this should give 5 to 24 448 at 0.2. Kmax. Blue and red falling on a certain cathode produce photoelectrons. Maximum kinetic energy. So lambda of red is greater than lambda of blue. So frequency of red is less than frequency of blue. Maximum kinetic of the emitted photon is higher for blue light. That's correct. Frequency is higher. Stopping potential is higher for red dot. No. Work function of red photon is higher for blue. No. It is same. Work function same for blue and red. Number of emitting photoelectrons is always higher for blue light. That we cannot say, right? Number of emitting, that depends on the intensity of the blue light. Hence it is always higher. So potentially same for more colors. So one is correct. The graph shows the variation of the maximum kinetic energy. So the variation of the maximum kinetic energy of emitted proton electrons from metal with frequency f, the incident radius, the work function of the metal is. So when this is, so we have K max is just minus, so this is the work function. So 1, 2, 3. So maybe we have to use a ruler. Anyway, so when this is at 2.5, at process 2.5, so 2.5. That's so y equal x minus c. The work function corresponding to the methods A and B are W1, W2 respectively. W1 is greater than W2. Two surfaces made of A and B are emitted separately using the monochromatic beam of light of frequency A. Which of the following graphs better expresses the variation of maximum kinetic energy of the emitted photon with frequency? That's a gradient is same. A is equal A max is equal HF minus phi. So gradient is same, M is same. So they should be two parallel lines, and since W1 is greater than W2, A should be the WA should intersect below than B YX. Let's take a second. ABC are three metal threshold wavelengths. Lambda A 0.3, lambda B 0.28. For photoelectric means the photons of frequency are incident on each of the metal. The photoelectrons are emitted. So using, you can find the wavelength of the photon. Lambda is COF. C is 3 in 10 to the power 8. But F is 2.5. In micro, it is 0.25 micrometers of the lambda of the photon. So to emit electrons, lambda should be greater than threshold. Threshold value should be greater than lambda. And it is the opposite of because threshold frequency should be less than the frequency. So the wavelength behaves in opposite way inversely for the frequency, layer frequency. So lambda A from A, electrons would be emitted. B, correct? C, no, from A and B. From A and B, emitted. Photoelectric currents are emitted. A and B metal photoelectric current are emitted. That part of orbiting satellite is coated with metal that has work function of 1 eV. Let's say 1 eV. The Planck constant is 4.1 10 to the minus 14 s, and the speed of light is t in 10 to the power 8. What could be the longest wavelength of incident sunlight that can eject an electron from the metal coating? Let's get this as one at one electron volt. So Hc over lambda max is equal work function. Hc over work function 4.1 in 10 to the power 5, 3 into 10 to the power 8, 1 eV. So these are given in eV. EVS MS minus 1. So EV get cancelled out. Let's get cancelled meters. Nanometers. A metal surface is illuminated with monochromatic blue, red, and yellow light. Monochromatic blue, red, and yellow light separate the following statement. Lambda red is greatest, then lambda yellow, then lambda blue. If red light ejects photoelectrons, then blue light should also eject photoelectrons. Frequency high, frequency varies in opposite way. Yes, so if red light ejects photoelectron, then blue light should also eject photoelectron because it's sufficient. Blue light having the highest frequency. Yellow light ejects photoelectron, the red light should also that's blue light ejects photon, then the red light should also eject photon. That's a reason. Only A is true. Right, so in today's session, we learned about a new phenomena called photoelectric effect, which could not be expressed. The photoelectric effect, which cannot be expressed using the traditional theories related to the waves, uh, oscillation waves. So new concept called photons and or the electric, the energy packets are introduced here using Max Planck, and on top of that, finally Einstein have formulated this equation to find the to which governs this photoelectric effect. The energy of a photon is equal to the addition to work function. Work function is the energy required to break the bond. So that depends on the metal plus total maximum kinetic energy gained by the electron. Right. So in the next session, we will look at this behavior of waves as matters. So the wave nature of matters. So we uh, can look at the behavior of waves as some other perspective related to matter. So that we will discuss in next session. So thank you.